I was introduced to the Fick's law of diffusion and theory of mass transfer when I followed the lectures of Professor Man Mohan Sharma at the University of Bombay. Here is a picture of M.M. Sharma talking to Professor A.B. Pandit, currently the Vice Chancellor at the Institute of Chemical Technology. And this is a fictional account of a conversation between the two. I was standing close by, and I can vouch that this is not exactly the conversation between the two. However, in my fictional account, I have Professor Pandit asking, is Fick's law reliable? And Professor Sharma replying, it works very well for sour gas absorption in amine solutions. Actually, what they were talking about is what are we going to have for dinner tonight? I'm going to address this question, is Fick's law reliable, in my presentation today, and to highlight the shortcomings of the Fick's law of diffusion, I start my discussions in the Antarctica. Here's a picture taken in Antarctica showing fortresses of ice containing nearly pure H2O in contact with seawater that contains salt. The question arises why there is no diffusion of salt from seawater into the ice fortresses. In order to resolve the paradox observed in Antarctica, let us resort to the Gibbsian thermodynamics of phase equilibrium. For two phases that are in thermodynamic equilibrium, the chemical potential of any component must be equal in either phase. The chemical potential of any component is written as the chemical potential in some standard state plus R times T times ln of the activity, where the activity is the activity coefficient times the mole fraction. The chemical potential is the partial molar Gibbs free energy, where the Gibbs free energy has two contributions, the enthalpic contribution and the entropic contribution. These represent respectively the unmixing and the mixing tendencies when the system is subject to perturbations in composition. S is the entropy and is given by the Boltzmann equation. S is K ln W, that is engraved on his tombstone in Vienna. The symbol W stands for Wahrscheinlichkeit. You will note that Josiah Willard Gibbs and Ludwig Boltzmann were contemporaries. The red line shown here is a plot of the Gibbs free energy for the ice crystals, plotted as a function of the mole fraction of sodium chloride. The blue line is the Gibbs free energy of seawater plotted against the mole fraction of sodium chloride. The seawater contains significantly higher concentrations of sodium chloride. The The phase equilibrium between the ice fortresses and seawater is described by the common tangent between the two curves. And this tangent intercepts the x1 equal to 0 axis at this point, which represents the chemical potential of water in the ice that is also equal to the chemical potential of H2O in seawater. At the other end, the common tangent intersects the x1 equal to 1 axis, at which the chemical potential of NaCl in ice is equal to the chemical potential of NaCl in seawater. What we note is that there is equilibrium between the ice fortresses and seawater, but this equilibrium corresponds to significant differences in the salt concentration in the ice fortress and in seawater. This example underscores the fact that the mole fraction differences or mole fraction gradients are not the proper driving forces for molecular diffusion. In view of the arguments presented in the foregoing slides, we must abandon the commonly used Fick's law to relate the molar diffusion flux to the gradient of the concentration. In setting up the proper flux driving force relationship, we have two choices. The first one is to adopt the Onsager formulation that was coined by Lars Onsager, who won the Nobel Prize for Chemistry in 1968. In his seminal paper in 1945, he wrote, "The theory of liquid diffusion is relatively undeveloped. It is a striking symptom of the common ignorance in this field that not one of the phenomenological schemes that are fit to describe the general case of diffusion is widely known. In the Onsager formulation, the flux is related to the gradient of the chemical potential by defining a matrix of Onsager coefficients L. For an n-component mixture, we have n-1 independent fluxes and n-1 independent chemical potential gradients that are considered to be the proper driving force for diffusion. The matrix L, that is n-1 times n-1 dimensional, is asserted to be symmetric, and this symmetry relation is dubbed the Onsager reciprocal relations.